Use the first and second derivatives of f of x, which is equal to e to the power of 1 over x, together with asymptotes to sketch its graph. So, first thing we want to do is we want to take a look at the domain. So, the domain of the function, so the domain of f we can see here is that x is all real numbers except x cannot equal 0. Okay, the reason why is if we plug in 0 into that function, it's going to be e to the 1 over 0. So we know that's the domain. Okay, now the next thing we need to do is we need to then check for vertical asymptotes by computing the left and right limits. Okay, so what we're going to do is, well, in this case, as x is approaching 0. Okay, so if we're looking as x approaches 0 from the right, and as x is approaching 0 from the right, then we know that t is going to equal 1 over x, which is the exponent, which is going to be approaching infinity. So if we take the limit as x is approaching 0 from the right of e to the 1 over x, which is equal to the limit as t approaches infinity of e to the t, which is equal to infinity. So what this shows is that x equals 0 is a vertical asymptote. Okay, so now what we want to do is we want to check what happens when x is approaching 0 from the left. Well, then t is going to equal 1 over x, which then is approaching negative infinity. So we have the limit as x is approaching 0 from the left of e to the 1 over x, which is then equal to the limit as t is approaching negative infinity of e to the t, which is therefore equal to 0. And so we can also then say that as x is approaching positive or negative infinity, then we can say that 1 over x is approaching 0. So if we take the limit as x is approaching positive or negative infinity of the function e to the 1 over x, well, then that becomes e to the 0, which is equal to 1. And so therefore, this shows that y equals 1 is a horizontal asymptote. So now let's find the derivative of this function. So I'm going to move this over just a tiny bit. Okay. So in step number 5, we want to find the derivative of this function. So we know that the function f of x is equal to e to the 1 over x. Okay. So if we want to find the derivative of this function, we have f prime of x, which is going to equal e to the power of 1 over x. And now what is the derivative of 1 over x? We know the derivative of 1 over x is negative 1 over x squared. Okay, so now that's the first derivative. Now we want to find the second derivative of this function. So using the second derivative of this function, we're going to use the product rule. So what we want to do is we want to take the derivative of e to the 1 over x. So we have e to the 1 over x times negative 1 over x squared times negative 1 over x squared. And then plus we have e to the 1 over x. And now we want to find the derivative of negative 1 over x squared, which is 2 over x cubed. Okay? And so keep in mind here that if we have 1 over x, this is equal to x to the negative 1, which becomes negative 1 times x to the negative 2. And then if we want to find a derivative of negative 1 over x squared, well, this is the same thing as negative x to the negative 2, which makes this positive 2x to the negative 3, okay, which is how we're getting those derivatives. Okay, so now let's simplify this a little further by multiplying everything out here. So the second derivative, f prime of x, is going to equal e to the 1 over x in the numerator. If we take a negative times a negative, it's a positive. In the denominator, we have x to the 4th. And then plus, we have 2e to the 1 over x cubed. Okay, now we want to find a common denominator. So we should see that the common denominator is going to be x to the 4th. So we have x to the 4th plus over here x to the 4th. So going this route, we know if we multiply this by 1 and this by 1, this gives us e to the 1 over x. Multiply this by an x and multiply this by an x gives us 2x e to the 1 over x. So therefore, if we then complete the second derivative, then we should see that they both have e to the 1x in common. So we're going to have e to the 1x, and what's left is 1 plus 2x over x to the 4th. So there is our second derivative, and there is our first derivative, and then there is our function. So now what we're going to do is we're now going to take a look at finding the critical numbers. So if we want to find the critical numbers of the function, or in this case, the critical numbers of the first derivative, so we know that the first derivative, f of x, is equal to negative e to the 1 over x divided by x squared. Okay, so let's explore this. Okay, first and foremost, we know that it's negative. So if it's negative, then we need to look at the numerator. So if we look at the numerator, if we have e to the 1 over x, okay, this is greater than 0. And we also know that x squared is greater than 0. But we also know the restriction tells us that x cannot equal 0. But since it's negative, okay, that tells us that f prime of x, or the derivative, is going to be less than 0. So if the derivative is going to be less than 0, then it tells us that on the interval, okay, we know that 0, okay, cannot be included, so we're going from negative infinity to positive infinity. So that means that f prime of 0, or sorry, f prime of x, excuse me, f prime of x is going to be decreasing here, and it's also decreasing here. So that means that it's going to be decreasing on the following intervals: from negative infinity to 0, and from 0 to infinity. Okay, so that tells us that we don't have critical numbers. So no critical numbers, which means that we have no local maximum or minimum values. Okay, now let's take a look at the second derivative. If we look at the second derivative, we have e to the 1 over x times 1 plus 2x over x to the fourth. Okay, likewise, okay, when we take a look at this function, we can see that we have e to the 1 over x is greater than 0. And we also know that x to the fourth is greater than 0. Now, since this function is positive, then that tells us that f, or the second derivative of x, is going to be greater than 0. And so now we want to take a look at what happens when, okay, so when, if we look at this 2x plus 1, and we're going to set that equal to 0. Okay, saying that's equal to 0, if we solve for x, x is going to equal negative 1/2. Okay, provided that x does not equal 0, because if it equals 0, then it's just going to make the entire thing undefined. Okay, so let's take and find out where it is concave up and where it is concave down, and then we want to determine where is there a possible inflection point. So we have negative 1/2, okay, and we know that we have these regions, so let's take a look at these regions. Okay, so we have region 1, which goes from negative infinity to negative 1/2. Then we have region 2, which goes from negative 1/2 to 0. And then we have region 3, which goes from 0 to infinity. Okay, so in region number 1, we can pick a testing point. So let's pick a testing point of negative 1. All right, so let's go ahead and put that in our calculator. So using Desmos, okay, what we did is we put this function, a second derivative, into the table. And so we're going to plug in negative 1. Plug in negative 1, it gives us a negative answer. So it's negative here, which tells us that f prime of x, f double prime of x, second derivative, is less than 0. Okay, let's go to the second. So we're going to use, let's say, negative 0.25 or negative 1/4. Okay, so let's go ahead and plug that in. So we have 1/4, and that gives us a positive value. So the answer is going to be positive. And if it's positive here, then we know that f second derivative is going to be greater than 0. And then let's take a look at the third region. So we're going to pick x equals 1. So if we plug 1 in here, we get a positive value. So therefore, it's positive here, which tells us that the second derivative, x, is going to be greater than 0. Okay, so what does that tell us? Well, it tells us that the following. We can see that in the interval from negative infinity to negative 1/2, okay, so from negative infinity to negative 1/2, it is concave down. And then from negative 1/2 to 0 and 0 to infinity, the second derivative is greater than 0. So that's concave up. And then we need to determine if there's an inflection point or not. So is there an inflection point? Well, if we look here, we go from negative to positive, so there is an inflection point at negative 1/2. Okay, so if we plug in negative 1/2 into that function, so we know that the inflection point is at negative 1/2, so when x is equal to negative 1/2, and so let's plug that into our function. So f of negative 1/2, which is our function, is going to be e to the 1 over negative 1/2, which ends up being e to the negative 2. So the inflection point is going to be located at negative 1/2 and then e to the negative 2. Okay, so let's go ahead and graph this. Okay, so first thing we know is we know that we have a vertical asymptote at x is equal to 0. So we can go ahead and put x equals 0. Okay, and so if we want, we can then go ahead and make that a dashed line, so we know that's a vertical asymptote. Okay, and then we also have a horizontal asymptote at y is equal to 1. And so again, let's go ahead and make that into a dashed line so we know that that's a horizontal asymptote. Okay, so now we know where our horizontal asymptotes are. We're going to go ahead and copy this. So I'm going to go ahead and copy this graph. Okay, so, and then we can finish the graph here. Now, yes, we can graph this by plugging it in, but let's discover what we're supposed to do here. Okay, so we know that to sketch the graph, we got the horizontal and vertical asymptotes. Okay, now, again, looking at all the parts that we talked about, the information concerning limits and the fact that the function is decreasing on both from negative infinity to 0 and from 0 to infinity. So that means that we have, at the vertical asymptote here, we know that we have this decreasing function here, and we know it's going to be decreasing here. Okay, and then in addition, we know that we have y equals to e to the 1 over x, so we know that it's going to be decreasing from here to here, and then along the horizontal. Okay, so now what we want to do is we want to finish the sketch by graphing the inflection point. Well, the inflection point is located at negative 1/2 and e to the negative 2. So that we can go ahead and pick that point. So let's go ahead and put that on our graph. Okay, so we have negative 1/2 and e to the negative 2. Okay, so we can see that point is somewhere around there in between that 0 and negative 1. So it's a little bit lower. So let me go ahead and move that this way. So we know that here is the inflection point. So there is the inflection point. So what that means is we then have a graph that's going to look like the following. Okay, we have a graph going in this direction, and then we have this graph going in that direction. Okay, so if you take a look there, okay, let's go ahead and graph that. So if we graph our function, and again, that function is e to the power of 1 over x. And then you can see here how it travels through the inflection point, and there is our horizontal and there is our vertical asymptote, which matches the graph that we just graphed here.